Three collection types dominate Go programs: arrays, slices, and maps. Arrays are simple but rigid. Slices are what you'll reach for constantly. They're dynamic, efficient, and the foundation of most Go APIs. Maps give you key-value lookups in O1. Understanding how they work internally makes you a better Go programmer because you stop guessing about when copying happens, when appending reallocates, and what nil really means. An array in Go has a fixed size that is part of its type. You can read and write by index, range over them, and call len. That's about it. The critical thing to know: 5int and 10int are completely different types. You cannot pass a 5int to a function that expects 10int. And arrays are value types. When you assign an array to a variable or pass it to a function, Go copies every element. This copy-on-assignment behavior makes arrays predictable but expensive for large data. That's why, in practice, arrays rarely appear directly in Go code. You almost always work with slices instead. So why do arrays exist? Because slices are built on top of them. Every slice you create has an underlying array behind it. A slice is a three-field struct: a pointer to an underlying array, a length, and a capacity. The pointer tells Go where the data lives. The length tells Go how many elements you're currently using. The capacity tells Go how much room is available in the underlying array before a new allocation is needed. Creating slices. A nil slice and an empty slice are different. A nil slice has a nil pointer and 0 length. An empty slice like int has a non-nil pointer and 0 length. For most practical purposes, they behave the same. You can range over both, call len on both, and append to both. But nil comparison only works for the nil slice. Use lens == 0 to test emptiness reliably for either. Append is how you grow a slice. Notice you must assign the result back. Append may return a new slice pointing to a new underlying array if the capacity was exhausted. If there's capacity remaining, the same underlying array is extended and the same pointer is returned. If capacity is exceeded, Go allocates a new array, typically doubling the capacity, copies the elements, and returns a new slice header. This is why you always write s=append s, rather than just append s. When you know in advance how many elements you'll need, pre-allocate. This avoids repeated allocations and copies as the slice grows. You can create a new slice from an existing one using slice expressions. The critical fact: these subslices share the same underlying array. No copying happens. It's just a new three-field header pointing into the same memory. This is efficient. Subslicing an n-gigabyte slice is O1. But it means mutations propagate. When you need an independent copy, use copy. Copy copies min, len, dst, len, src elements. After this, dst has its own underlying array. Mutations to dst don't touch src. A practical pattern: append preserves the safety because append to a full slice allocates new memory. The 3-index slice s, low, high, max lets you control the capacity of the resulting slice. Setting max == high forces the next append to allocate, protecting the original. Maps are Go's hash table. They map keys to values with average O1, insertion, lookup, and deletion. The key type must be comparable. Strings, integers, bools, arrays, and comparable structs work. Slices, maps, and functions cannot be map keys. Basic operations. Reading a missing key returns the 0 value silently. That's convenient for counters but dangerous when 0 is meaningful. The two-value form tells you whether the key actually exists. OK is a bool, true if the key exists. This pattern shows up throughout Go's standard library. Maps are reference types. When you pass a map to a function, you're passing a reference, not a copy. The function can modify the caller's map. Map iteration order is deliberately random. Go randomizes it to prevent code from accidentally depending on order. If you need ordered output, collect the keys, sort them, then iterate. Maps are not safe for concurrent use. If multiple goroutines read and write the same map simultaneously, you'll get a data race. We'll cover synchronization in the concurrency episodes. To clear all entries from a map at once, use the clear built-in. Clear was added in Go 1.21. It's equivalent to deleting every key manually but expressed in a single call. Note that the map itself remains non-nil and ready to use, it just has 0 entries. 3 patterns you'll write over and over. Counting. Maps 0 initialize missing keys, so incrementing works without a check. Deduplication. Use a map, t-struct, eu as a set. Struct. Uses 0 bytes filtering. Build a new slice with elements matching a predicate. Grouping. Accumulate values under a key using a map of slices. This is one of Go's most elegant idioms. On the first insertion for a given city, by city p.city returns nil, the 0 value for a slice. Append on a nil slice works fine and allocates a new backing array. No need to check whether the key exists first. The pattern generalizes to any grouping operation. Logs by level, orders by customer, events by date. Arrays are fixed-size value types rarely used directly. Slices wrap arrays with a 3-field header, pointer, length, capacity. Create with a literal make or by slicing. Append may reallocate, always assign the result back. Subslices share the underlying array. Use copy when you need independence. Maps are hash tables. O1, operations, reference semantics, unordered iteration. Initialize before writing. Use the to-value form to distinguish missing keys from 0 values. Not concurrent safe. Patterns to memorize. Increment missing map keys directly. Use map, t-struct, 4 sets. Filter with a predicate function. Episode 11 covers strings, runes, and bytes. Go's handling of Unicode text. See you there.